One consideration when you're doing these types of assays is that you have to be a little bit cognizant of some sort of non-specific background. So say, for example, you have a pellet of proteins and DNAs, and who knows what else is in your extract. You might get a certain amount of radioactivity in the pellet that is just simply trapped, rather than really representing incorporation into a polynucleotide. It could just basically be caught up with all the other material in the pellet. So this was a major concern for them because the level of radioactivity that they were detecting in the pellet was just so small, 0.01%. So they applied a very nice trick, which was that they actually took their pellet and then resuspended it. So all the material is floating around now, and then they treated it with DNase. And DNase is an enzyme that cuts up polymers. Okay, so the enzyme will degrade polymers of DNA back to nucleotides, and then they did the same thing. So they added in trichloroacetic acid, and then they centrifuged. And then they got this, a supernatant and a pellet. And when they did this, the radioactivity was now all in the supernatant. So that indicated to them that the radioactivity was in the original pellet, because they could treat the DNA polymer with DNase, and it would resolubilize so that they can make it soluble again. So this was sort of the key evidence that despite the inefficiency of the reaction, they really had something going on here. So this was the sort of the nuts and bolts of their initial DNA polymerase reaction. It allowed them to establish that there was at least some DNA polymerase activity in this E. coli extract. But now, of course, in order to characterize the properties of this DNA polymerase, they wanted to have the DNA polymerase on its own. They didn't want to be studying it in the context of a whole bunch of other proteins, and these proteins that might have other activities that would interfere with them being able to understand the actual properties of the DNA polymerase. So really now, this is where the game begins. You ask yourself, I have this complex mixture of thousands of proteins. I have an assay, but how do I get my protein out of this complex mixture? So, all right, so the first thing they needed to do, or maybe, well, they didn't need to do, but were able to do, was actually make some improvements. And the improvements were actually in the source material. So source improvements. And basically just to make the whole assay better, because we all know better is better, right? So there's no arguing about that. So along the way, Kornberg and Sims, purified an enzyme that actually carried out this reaction. So it would use thymidine, and in the presence of ATP, lead to the creation of DTMP plus ADP. Okay, and this enzyme, they named it thymidine kinase. Okay, so basically the enzyme, if you remember back to your enzyme section in Biochem 210, would basically phosphorylate the thymidine and give the nucleoside monophosphate. And what they found was when they used, remember in the original assay they had thymidine, but if they used DTMP or thymidylate, the assay actually worked better. So they got more incorporation of radioactivity into their acid-insoluble pellet. So if we had this amount of activity with thymidine, we had an increase in the activity with thymidylate. Okay, so an increase in activity. So this actually, the reaction worked better. Okay. So they got more incorporation, and again into their acid insoluble pellet. So this worked well, and that gave them, you know, sort of an improvement in terms of the level of activity over background that they could detect. So that was good. And then it also allowed them to do another thing, which was originally, remember we had C14 as our radial label, or thymidine. So this was our original. And if you recall, this had low radioactivity. Okay. So it's fairly low. So having a handle on this reaction, however, allowed them to actually label their substrate with P32 instead. And again, what did they do? They used thymidine in the presence of P32 that was gamma phosphate labeled ATP. Okay, and just to sort of remind you, when we talk about ATP, so we have adenosine and our 3 phosphates. They're all labeled. So this is the alpha phosphate, this is the beta, and this is the gamma, and this is where our P32 label comes in. So basically, when we have this reaction occurring, our gamma phosphate would get transferred onto the thymidine. So then you would actually create alpha P32, radial labeled DTMP, plus ADP. Okay. So the yield is P32 labeled DTMP. So now they're able to use a P32 labeled substrate in their reaction. And what they found was that the monophosphate actually works better than the thymidine. And they found that they had a higher level of radioactivity. So improvements are improvements, right? Okay, so again, this was an improvement in the reaction. Second thing that they found was that they could convert DTMP to the triphosphate using a partially purified enzyme mixture. And what was in this mixture has at least 2 functionalities. The first is called nucleotide kinase. And what this nucleotide kinase does is it will label the monophosphate to the diphosphate. So again, let me just write out this reaction. DTMP plus ATP, and we have our nucleotide kinase, so that we generate TDP plus ADP. Oops, ADP. And plus the second functionality was that there was also a nucleoside diphosphokinase, and what that enzyme reaction that it catalyzes is taking DTDP plus ATP. So then we have nucleoside diphosphate kinase to produce DTTP plus ADP. Okay, and then again, you could test these different substrates in their reaction, and they had already established that TMP worked better than thymidine. And when they used the triphosphate, it was actually vastly superior. So they inferred from this that the DTTP, the triphosphate form of the nucleoside, was much more likely to be the relevant substrate of the DNA polymerase than either thymidine or the monophosphate. So basically they tested different substrates, and they concluded that the DTTP was the best nucleotide for polymer synthesis. Okay, so now we're in a now they were in a position where their final assay. So again, let me just write this down here. Consisted of P32 alpha labeled DTTP, ATP, magnesium, and extract. Okay, and I would definitely like you to consider how would you make this DTTP form, this triphosphate. Okay. All right, so we have basically one more concept to go. So they have a complex mixture. They're interested in identifying a single protein, presumably within this complex mixture. And so to purify this DNA polymerase activity, they undertook a process that is referred to as fractionation. And the idea of fractionation is that you use different physical properties to separate components of a complex mixture from each other. Okay, so let me just write that definition down. So use different physical properties to separate components of a complex mixture from each other. Okay. Then once you have the components separated into different pools, you apply your assay to the input material and to each of your pools, and then you see which pool has the activity, and presumably the pool now has lower complexity than the original mixture did, and then you take that pool and apply a different mode of physical separation, and you basically repeat and then turn the wheel until you actually have a single polypeptide or a single component remaining in your final pool. So we'll just do a quick example here. So we have a complex mixture, and I'll just draw a test tube with our solution, and say we have 3 different proteins. So we have a triangle, a square, and a circle, and for argument's sake here, our squares are DNA polymerase. Okay, so if we apply the DNA polymerase assay to this mixture, yes, there is extract, and to this extract there is activity. So then what we're going to do is actually take this mixture and apply it to a fractionation column. So these columns tend to look like this. So here's our fractionation column. Okay. So let's just say, for argument's sake, this fractionation column will separate proteins based on the physical properties of pointiness. So in this fraction, the least pointy thing, the circle, comes out first. And then the second fraction, the second most pointy thing, and then the triangle comes out in the last fraction. I'm sorry, the triangle comes out in the second fraction, and then the final fraction, the square, comes out. So basically we can collect fractions here. So the least pointy thing, the circle, comes out first, and then we would have our triangle come out in the second fraction, and then finally we would have our square, or our DNA polymerase, come out in the third fraction. So in this simple setup, we've gone from a complex mixture to basically a purified protein. So they were anticipating that the DNA polymerase would be a protein. And using this type of fractionation, they would be able to separate it into a single fraction that's collected off the column. So basically what you do, you now apply your DNA polymerase assay to each of these fractions, and of course you would see that there wouldn't be any activity here, there wouldn't be any activity containing the triangle, but there would definitely be activity with the fraction containing the square. So DNA polymerase activity. Okay. So basically we've gone from a simple setup where we've gone from a complex mixture to a purified protein. So the idea sort of remains the same. So they basically were assuming that, or anticipating that the DNA polymerase would be a protein. So DNA polymerase was a protein. So based on that, what kind of other physical properties might you exploit to separate proteins from each other? So one good example would be using properties like hydrophobicity. So that's a good one. That's a very sophisticated one, actually. Any other ideas? You could definitely use molecular weight, okay, based on size. Do all proteins have the same charge? No, of course not. So you might separate them based on that charge. Is the charge of all proteins or of a given protein the same at all pHs? No. So, you know, again, you have to think about the optimal conditions when you're trying to determine pH. Another thing is you can ask, are all proteins soluble under the same conditions? No, of course not, right? So we can look at differences in solubility. Possibly in different organic solvents. What about the specific properties of the protein that we're interested in, like in terms of what kind of things they might bind to? So maybe affinity. So if we're looking for a DNA polymerase, what sort of thing might it bind to so you can take advantage of it? Or you can hypothesize something about the protein. So you might hypothesize that it likes to bind phosphates. Okay, or different, you know, nucleosides. So DMPs or DTPs, DNTPs, sorry, or even DNA, right? So basically, just to summarize, there's lots of different means available to ask about the physical properties of a protein and use them to fractionate such that you can purify your protein of interest on its own. Okay, so now let's actually delve into the process, or what they actually did in this purification scheme. So here's just a very simple schematic of their fractionation scheme. So fractionation scheme. And basically they were starting with an E. coli extract. And the first thing they did was they added streptomycin to the extract. And this is a positively charged molecule. And it precipitates DNA. Okay, and so they could then, again, by centrifugation, so we'll do some centrifugation, separate a supernatant, and this is the S fraction, supernatant, from a pellet, or the P fraction. And basically then take those two different fractions and apply their assay rate. So if we look over here and we look at the polymerase activity as measured by DTTP incorporation into DNA, obviously the extract had activity, and that was their starting material. And here came the first surprise, actually. Their supernatant fraction, or the S fraction, had no DNA polymerase activity. Likewise, when they assayed the P fraction, or the pellet, there was no DNA polymerase activity. So this was kind of curious, right? They separated the the E. coli extract into two fractions, and neither of them had it. So the question was, did it disappear? Well, they were kind of clever about this, and as a sort of a control for it just disappearing, they took their S and P fractions and added them back together and repeated the assay. And when they did that, they found that they could actually get DNA polymerase activity. Okay, so what you can actually infer from this is that you have two fractions, and neither of them is sufficient for DNA polymerase activity. But if you combine them now, you actually see activity. Okay, so then you get activity. All right. So again, you can infer that you need both for DNA polymerase activity. Okay, so that was quite interesting in terms of what they found between the S and the P fractions. Okay, so so the rest of the scheme is just sort of a skeleton of what they found upon further fractionation of these initial components, both the S fraction and the P fraction. And what they found was there was actually a lot of stuff that was required. So basically the S fraction had two important components. One, it had a whole bunch of mixture of nucleotides, and then it also had these kinases, these protein kinases that I just described, that convert the nucleoside monophosphates to their triphosphates. Okay. So the S fraction had DNMPs, and it also had the kinases that will catalyze the conversion of the monophosphates to the triphosphates. In addition, the P fraction also had two critical components, one of which was the DNA polymerase. Okay, once again, a huge sigh of relief. The other component, curiously, was DNA. So this kind of raises an interesting question. Why do you need DNA in order to make DNA? And this was something that they had not really anticipated. And additionally, the reaction already contained DTTP. So how come they needed the other 3 nucleotides or nucleoside triphosphates? So that was also unanticipated. So that was the big question here. Why do you need DNA to make DNA? And the second was, why do you need all the other 3 DNTPs? All right, so their initial hypothesis was that what was basically happening in the reaction was that existing chains of DNA were actually being extended by the DNA polymerase, such that the DNA polymerase would use the DTTP, and the reaction would basically just stick a DT on the end, and again stick another one on the end, and keep this cycle going until it ran out of DTs. However, there were a bunch of properties of the characterization that ran counter to this type of model. And the first is, if this were true, why on earth would you need the other 3 DNTPs, right? So again, if this hypothesis were true, if true, why do you need the other 3 NTPs? DNTPs. So the other 3 DNTPs. Okay, so that's point number 1. I mean, that made no sense really, right? The second thing is, if they looked at the DNA that was in the DNA fraction, and they measured its composition in terms of AT to GC ratio, they found that the newly synthesized DNA had the same composition. So that's point number 2 here. And that also didn't make sense, right? If all you were adding or doing was adding DTs, then the AT to GC ratio should of course go up, not stay the same, right? So that was kind of bizarre. And then they found that if they monkeyed with the concentrations of the 4 DNTPs, it basically had no effect on the composition of the final product. So that's point number 3. So no effect on final product. I mean, basically, if you were just tacking things on at the end and you reduced the DCTP concentration, for example, by 10-fold, you might expect a 10-fold less DCTP to be in your product. So basically, by combining these 3 observations, what they suggested is shown here at the bottom of the slide, which is what they were saying. It was just basically a templated enzymatic synthesis of DNA. And this kind of templated or template-directed synthesis was totally unprecedented in biochemistry. So basically, if you combine points 1, 2, and 3, it suggested a template directive for DNA synthesis. So of course this was quite striking. So now they're in the position where they've got their purified DNA polymerase, and now being biochemists, they can actually just go to town and figure out what the properties of this thing are, what kind of things is it capable of doing in an in vitro setting, and then use this information to hopefully figure out what's going on in an in vivo setting. So they now have this purified DNA polymerase 1, and now they can start to ask some biochemical questions about what it can and what it cannot do. And as always, almost always the cases in biological sciences, every answer to every question poses new questions, which we refer to as complete lifetime employment, if you want to think of it as in another way. So the first thing they discovered is that